We present DINO-Tracker, taming Dino for self-supervised point tracking in a single video. Tracking is a long-standing task in computer vision, spanning various representations and use cases. Beyond sparse tracking, establishing point-wise correspondences opens the door to more precise downstream tasks, such as animal behavior analysis, motion analysis, and video editing. Given a video and query points as input, our tracker outputs the position of each point in all frames, producing motion trajectories along the entire video. Recently, supervised methods for point tracking have shown significant progress. However, these methods are typically trained on synthetic datasets consisting of moving objects in unnatural configurations and contain non-realistic textures, which presents a challenge when applied to real-world videos. While training on real-world data might resolve these issues, annotating real videos with point-wise correspondences is costly, and annotated data is currently limited to evaluation purposes. In addition, existing models are still limited in their ability to aggregate information across the entire spatial temporal extent of a video. For example, CodeTracker, which aggregates information from a spatial neighborhood by jointly tracking multiple query points, can only process a limited temporal window due to computational constraints. In contrast, Tapier, which processes the entire video, only tracks one query point at a time. Addressing these challenges, OmniMotion proposes a test time optimization framework, solving for the motion of all video pixels simultaneously and bridging the gap between synthetic and real data. However, OmniMotion heavily relies on optical flow and lacks a visual prior, which limits its ability to generalize, particularly when tracking occluded regions where motion supervision is sparse, as illustrated in the example below. To bridge the gap between test time training and learning from large-scale data, we propose DINO-Tracker, a tracker optimized on a single input video while leveraging an external visual prior. Specifically, we utilize the spatial features of a pre-trained Dino V2 model, which has been shown to capture fine-grained semantic information. The combined framework achieves state-of-the-art results, especially in tracking past long occlusions. Our feature matching based model operates as follows. To track a query point XQ in frame T, we first compute the cost volume between its sampled feature and the target feature map. The final track position is then estimated based on the points in the vicinity of the maximum location. Our feature extractor combines the pre-trained Dino V2 model with our CNN-based Delta Dino, refining Dino's strong semantic features for temporal consistency and precise localization by predicting residuals that adapt to the test video's motion, ensuring long-range tracking. Finally, to improve precision, we refine the heat map with the CNN and apply a soft argmax for accurate position estimation. We train DINO-Tracker using two complementary signals extracted from the test video. Optical flow, which provides precise subpixel matches but is less effective for long-range supervision due to occlusions and error accumulation, known as drifting, and feature correspondences, extracted from a coarse spatial grid, which offer reliable long-term matches. We extract short-term tracks by chaining optical flow displacements between consecutive frames using Graph and checking for cycle consistency. During training, pairs of points are sampled from these tracks as supervision for our flow loss. To extract reliable feature correspondences between frame pairs, we compute their feature maps and identify mutual nearest neighbors, known as best buddies. During training, we use a contrastive loss to enhance the correlation between refined best buddy features, sharpening and localizing correspondences, and resolving ambiguities. Our unsupervised approach to occlusion prediction is based on two visibility signals: trajectory agreement, which we measure on a few anchor frames, and feature similarity between the query and tracked points. Only tracked points with high agreement and high similarity are marked as visible. Please see our paper for more details. Our resulting method tracks points accurately and smoothly in time, even in challenging settings. Note that while trajectories are shown for sampled points, our method tracks any point in the video. Moreover, Utilizing an external visual prior makes DINO-Tracker state-of-the-art in tracking across long and repeated occlusions. We compare our Delta Dyno CNN with two baselines, row Dyno and LoRa fine-tuning. The top row shows color-coded quarry points and tracks, while the second row highlights the correlation maps for the marked quarry point. Both baselines produce ambiguous, poorly localized features, especially for semantically similar objects, fisheyes in this example. In contrast, our framework uses CNN's inductive bias and smooth features to encode consistent representations, yielding well-localized, precise tracks. Thank you for your attention and visit our website for more results and code.